Hello, for our senior project, our team was tasked with designing a track and latching system for a rapidly configurable seating system, which would be implemented in transit vehicles. We are Nicholas Holman, Kai Kizan, Jacob Winkler, and Alex Kuznick.
Our design process spanned over 3 quarters at Cal Poly. We started with the problem statement and ideated on a solution. After we generated many possible solutions and ideas, we used Pew matrices and a weighted decision matrix to settle on one final concept. We refined this concept through initial FEA and rapid prototyping. This involved 3D printed models and rough models made of foam core and wood. Once we developed a refined model, we built a verification prototype to show the functionality of our design. This verification prototype was made from aluminum and was incorporated with the seat articulation team's design.
The goal for the final design of the track and latch subsystem is to support the weight of the seat, to entirely restrict movement when locked, and to restrict movement to a single degree of freedom when unlocked. An isometric view of the final SOLIDWORKS model is shown in the rightmost image. The latches constrain the seat vertically, while still allowing the system to slide when the double pin is unlocked. To lock the seat, the foot pedal is pressed down, which actuates the lever arm. Our designed lever arm has a built-in cam, which actuates the double pin between the locked and unlocked positions. When the lever arm is pushed down, a spring, aided by gravity, pushes the double pin assembly into the locked position. Conversely, when the lever arm is pushed up, the cam profile pushes the double pin assembly into the unlocked position. The cam follower assembly attaching to the double pin is shown in the inner right image, and the images on the left show the system when the double pin is locked and unlocked.
In the video on the left, we see that the seat slides along the track in the unlocked position. Binding can occur, which makes it much harder to move the seat along the track. This can be fixed with a back brace or a plate connecting both feet together to prevent the binding issue. Once the seat is in the desired position, you push down on the front bar to lock it in place. You may need to shake the seat in order to ensure that the lock is fully engaged. To be seen in the video on the right, once the seat is in the locked position, it is secure and cannot move.
To provide engineering justification for our design such that it would be safe and reliable for commercial use and applications, we performed a set of hand and finite element analyses on critical system components. Failure of these components will result in serious harm or injury to the user, and as such, they must be treated with the utmost care and concern. These analyses were based on SAE formulated stress loads that were evaluated further by a previous master's thesis done to support this project. We see that loads are placed both at the seat belt application location as well as the centroid of the seat. These two locations are then combined into an equivalent loading and statically equated to the two critical components, in this case, the latch body and the locking double pin. These components and the corresponding finite element analyses were backed up with hand calculations, which saw convergence both within the mesh study and between the hand calcs and finite element method.
With our prototype, we decided to test how easily the locking mechanism can be actuated and how easily the seat is moved on a clean and dirty track in order to simulate continual use and the debris that the system would see during its actual operation. In addition, we tested the total weight of the seat. Only the weight requirement was met, with our seat coming in far below the 70-pound requirement at 46 pounds. Meanwhile, it failed the locking actuation and seat translation tests. To pass these tests, the seat needed at most 5 pounds of actuating force and 10 pounds of force to move it. In the table shown, we see that the forces we acquired with a force gauge from testing are above these limits. This is due to improper cam design and lateral binding of the latches, which will be further discussed.
While our verification prototype turned out many positive results, there were also multiple lessons learned. The biggest lesson learned is that the double pin would not unlock due to the cam being too steep. We recommend a full redesign of the cam profile, as well as a detailed structural prototype to test actuation of the new cam. Another lesson learned was to avoid bending aluminum sheet metal, as we saw cracking even when the material was heated. We recommend ordering C-channel stock instead of trying to bend aluminum. The seat also has a large friction resistance when sliding the whole seat. We thus propose to increase the clearance in the track-to-latch profile to ensure smoother sliding. The large sliding resistance could also be due in part to the lateral binding of the latch feet. To remedy this, we recommend adding a rigid cross member between the seat feet to ensure a uniform sliding.
We would like to end with a big thank you to our sponsors Joe Mello, Rich Hollingsworth, and Cal Poly for their guidance and financial support with this project, as well as a shout out to the shop techs who helped guide us in manufacturing our model and our advisor Sarah Harding.